As we go during cross-country season.
What has hopefully become a habit to you guys, I'm just trying to remind you of what's actually going on. You are undoing operations away from the x. Otherwise known as inverse operations, yeah? So let's review these basic inverse operations. Okay, ln, yes, I know I threw in one that wasn't quite so basic, but still, I'm going to do it all on green. Let's review. What did you guys get at the end of the day when you undid each of the operations that were there properly? X is equal to e to the power of
4 plus
1. Which might be approximately, I didn't go to my calculator, sorry, I was just doing it. Now, hold on. Could you have undone some of these things in an improper order, still doing the correct inverse operations, but ending at a different answer? Meaning, could you have known that it was divide by and add and e, but you did it in the wrong order, so you arrived at the wrong answer? So does the order matter? Yeah, PEMDAS, right? You're undoing PEMDAS. However, the proper order would have been divide 3 first, e to get rid of the ln, and then the plus 1. Remember, I have to properly peel off the layers. Ooh. So did you correctly peel off the layers in the second one? Did you get x is equal to 96?
Yes.
What did you do first, those of you who got 96?
Multiply by 5.
Nice. The square root is not encapsulated in 5. It's totally separate. So multiply the 5. He's free. Then you have to do what to both sides to undo the square root?
Square.
And then to undo the plus 4? Is that good?
Okay.
So when the title of this new section that we're going to start today, is the inverse of a square matrix. P.S. homework not due tomorrow. I think it's due Thursday. I have to double check the calendar. Didn't get there yet. But when it says the inverse of a square matrix, what are we doing to that matrix?
Undoing.
Okay. No. Yeah. That's fine. Undoing. When did we know that we were done in 1 and 2? We didn't just get x. We got 1x. And what is 1 to any real number?
It's identity.
Which identity? No. Which identity? It has to do with an operation.
Gone.
Is it the additive, the multiplicative, the divisive, the subtractive? Which identity is it? Think about numbers. Caitlin, you got it. What is it? I thought you started to say it. Never mind. I thought you started to say
Multiplication.
Yeah. Because what's any number times 1?
It's
So it's the multiplicative identity because it's the one number if you were to multiply stays the same. So I got the x down to 1x, right? 1x is equal to. So what do you think I'm going to get a matrix down to? What's the multiplicative identity of a matrix?
One, 0, 0, 0.
What is Sophia trying to quote?
Identity
matrix. So I'm getting all of this down to 1x equals, but down here I'm going to get any matrix down to its identity. Wait a minute, have we done that before this year? Have we gotten a matrix down to its identity?
Yeah, like in the last chapter.
Row reducing, weren't we doing like, hey, let's get 1s, let's get 0s, let's get 1s, let's get 0s, let's get 1s, let's get 0s. Do you think our REF is going to come back?
Definitely. I like stoichiometry.
Oh, stoichiometry. Let's go grade section 8.2. You were adding, you were subtracting, you were multiplying. If legal, if possible. Hey, look, what's number 4's vocab? Look at that. Look at that.
I have one.
All right, number. Oh, yes, you do. You got it. Hid in, protected by, confidently preserved. Everybody up on the platform is trying to remind you of that. Number 4, identity. Number 8.
Someone showed me a picture of someone that drew a man. He has committed tax evasion and he's been convicted. Over here. Are you familiar with that, Miss D? Someone, Miss D, someone took a picture and showed me what happened.
Oh, people drawing on my
Yeah.
front board?
Yeah, and it was
Oh.
kind of scary.
There's scary things that get drawn on my board all the time. That's what I do. Oh, yeah, that was.
Yes, filthy facts. And bro, you can do the facts about that.
The little things. All right, so 8x is equal to -4, y is equal to 9. Number 32. Number 32 is at the very end down here. Do you guys get, can I read it to you? Tiny?
Yeah.
-8/3, 2/3, 8/3, 0, 4/3, -6. I could zoom in a little bit, sorry. I could zoom in a little bit. There you go. -8/3, 2/3, 8/3, 0, 4/3, -6. Good. You multiply 44. The answer was yes. The columns of one match the rows with the other, and you should have ended up with the resulting 3x2. Dot products, three-dimensional ones. You guys check it okay? Keep going. Number 62. Letter A was just a rewriting, which might have actually been kind of hard for you guys. I showed it to you, I just didn't take a long time on it. But it was separating all of the coefficients from all of their variables. It's kind of factoring out those variables, which is kind of crazy, but legal. And then making that doubly augmented, that augmented matrix with taking the variables and taking the constants, putting them together, and then, oh my goodness, our REF was a thing. I guess you could have used your calculator too, but they intended you to do it by hand, which is good review for today. And you should have ended at x is equal to 2, y is equal to 3/2, z is equal to 3/2. They were actually looking for the answer, the variable matrix. But I guess technically it's x1, x2, x3. X2, 3/2, 3/2. But for double checking purposes, you guys could have done RREF and known whether or not you were right, even though it was even, without even going to Slater. Oh, hey, that was the last even. Okay, do you want me to talk through anything? Odds, evens, showing work, interpreting directions?
For when you add or subtract matrices, they have to be the same shape, right?
Have to be the exact same order.
So there'll be no solution that are the same shape?
Right. Okay. Multiplying can be different shapes, but it's only if the middle orders match. Anything else? Sweet. Let's go play with inverses. And maybe you were listening carefully on Friday. Maybe you weren't. However, I did mention this idea of. How did I bring it up though? Because we haven't talked about inverses yet. I think I was talking about non-square matrices and how non-square matrices can't have identities. And if they can't have identities, they can't be undone. I think that's how I did it. If they can't be undone, I actually kind of told you what inverses do before today. I said if a matrix doesn't have an identity that matches, then it can't be undone. If it can't be undone, then any message coded with it could not be decoded. Anyway, all of that was just to let you guys know that at the end of this chapter, we get to be coding messages. Oh, we go. It's called cryptography. Now, matrices aren't the only way to encode. Most of your banking or your parents' banking information online is coded with prime numbers, which is this whole other method. The matrices took basic ciphers, 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 ways of encoding messages, and made them much more complicated. Anyway, we'll have fun with it. But inverses are the key. Inverses are the key. Now I can say today, if a matrix does not have an inverse, then a message could not be decoded. Or a message could not be encoded with that matrix and be decoded. But that'll be coming up in, I think, section 8.5, 8.6. I think 8.5 is the last section in this chapter. which means we have a test coming fairly soon. I think it's on the calendar next. I'll look it up. Okay. How could you do what the next example is asking? We have this definition of an inverse over here. We talked about inverse, undoing. Okay, we need to undo matrices. To undo matrices, we somehow get back to the identity. What would need to happen for B to be the inverse of A? What is this? What is a matrix times its inverse, or an inverse times its matrix? What do they both become?
They cancel out.
They are supposed to be each other's undoing. Right?
So if you multiply them by
F of G of X, G of F of X, that was the old-fashioned like composition way of talking about an inverse. So if you multiply a matrix times its inverse and the inverse times its matrix, both ways identity should appear. Yeah.
So if you multiply both, they all become the 1, 0.
That's exactly what we need to do. So let's go ahead and take our -1, 2, -1, 1 times our 1, 1, -2, -1. And when we multiply, hey, let's practice multiplication. Because why not? Probably need it. What goes into that first term, guys?
1.
-1 plus 2, right? It's -1 plus 2. We'll get back to it. The next one will be 2 minus 2, right? The next one's going to be oops. That was not meant to be a dot in the problem. Dangerous. That was -1 plus 1. And then -2. Wait, sorry. +2 minus 1. How does it work? Perfect. Usually with matrices, can you multiply in both directions and have them match?
Yes.
In numbers, yes, but with matrices?
So
Not commutative, yeah. So usually A times B does not equal B times A. However, I said there was one exception, and the one exception is a matrix with its inverse, because what if we were to go the other direction with 1, -2, 1, -1 times -1, 2, -1, 1? Going the other direction, multiplying the other way. -1 plus 2? 2 minus 2? Oh my goodness. -1 plus 1? And 2 minus 1. What do you see? A matrix and its inverse, an inverse and its matrix, they are each other's undo. Which, in life with like relationships, you should be aware of. However, in matrices, it's a good thing. And in math, needing to undo what has been done is also a good thing. In life, it's a bit dangerous. Although sometimes it's necessary, depending on what is being done. Therapy. Kind of does that, right? So going back to the definition really quickly, just so that if you wrote it down but didn't understand what it was saying, this is matrix multiplication. A matrix times its inverse, and an inverse times its matrix. Wait a minute. On your calculators, where is that matrix button again? Second. Technically, though, when we did it with numbers, didn't we see it was second reciprocal?
Oh.
Right? Didn't we see that? On your calculator, when you hit that little -1 button and you hit it with 5 -1, doesn't it give you 0.2?
Yeah.
How do I know that?
Because
1/5. It's doing the reciprocal, right? However, did you guys hear me accidentally keep calling it the inverse button?
Yes.
Can you put in matrix A to your calculator? Do you remember how to put in a 2x2 matrix? Remember how to make a 2x2 matrix? Put it in matrix A. And then can you guys go to the home screen and hit A with the reciprocal button? And my question is, with matrices, does it still mean reciprocal? Put in the A matrix. Do you remember how? Second, -1 button. Make it a 2x2. You guys going over to edit?
Yes.
What happens when you hit matrix A with the -1? So what does that button mean with matrices? inverse. Even your calculator is confused as to the -1 notation. 1 second it's a reciprocal, the next second it's an inverse. Well, or programmers were like, well, there's this reciprocal button. There's no real such thing as a reciprocal matrix, so we'll use it for inverse. Whatever. It made them do one less option in the matrix calculator menu. Wait, that's kind of cool. So that means that you can find inverses with your calculator if they exist, right? Mm-hmm. But we need to figure out how to do it without our calculator also. Sophia.
Is 0, 1, 1, 0 also? Or identity?
No. Because 0, 1, 1, 0 would flip the order of the entries. You can try it. The way you would try it is take 0, 1, 1, 0 and multiply it by like a matrix A or a matrix B, and you're going to have, I think, the same entries, but in different orders. I'm doing it quick in my head, but I'm pretty sure it's switching. Yeah, because you would do your first multiplication, and your first term would disappear, would be 0 plus C, it would switch around. Yeah, so you would get them in the wrong order. So we talked about what a matrix and inverse is, I should say, how we can recognize them. However, we have to talk about how to find them. But before we talk about how to find them, and guys, to be honest, there are like, I don't know, three different ways to find them. Let's talk about a couple of vocab terms real quick. So, a matrix that has an inverse can be called invertible or non-singular. Which is a little weird. So, why are you telling me a non-singular, like a non-vocab word, instead of telling me, okay, fine, singular, what's that? Then we'll know what non-singular is. Singular means no possible inverse. A singular matrix does not have a possible inverse. Down here at the very bottom, Bianca, you and I were kind of talking about this last week, at least in a way that leads up to this fact. Non-square matrices don't have identities, so therefore non-square matrices cannot have inverses. A non-square matrix can't multiply to be an identity matrix because all identity matrices are square, meaning the same number of rows, same number of columns, 5 by 5, 4 by 4, 3 by 3. All non-square matrices are singular. However, we need to add a quick little note in here. But, it's going to sound like a logic class, but not all singular matrices are non-square. All non-square are singular, but not all singular are non-square. What does that mean? I'm just going to like the animal kingdom. Do I want to go there? Give me a non-mammal.
Snake.
Okay. Reptile, snake. Let's go with snake. Okay. So, a snake. What's the snake called in Harry Potter? The really creepy one? No, but which one? Like the specific one, like Voldemort's.
Serpent. Oh, Nagini?
Yeah, thank you. Oh, but then it was a person that became a snake. That's weird. Let's not do that. Let's do...
The one from the Jungle Book.
Yeah, but I don't remember his name. I was trying to think of him first. Ka? Okay. So, we have Ka. All snakes are not mammals. True?
Yeah.
So all snakes are non-mammals, but are all non-mammals snakes? Okay, does that make sense? Like, you've used this logic in other places where you could understand this logic. You're not going to be as familiar with it here, but it's okay for us to say that all non-square matrices are singular. That's true. All non-square matrices cannot have an inverse. However, there are other matrices that cannot have an inverse as well, meaning there are also singular square matrices. And so a question that we need kind of just like rolling around the back of our heads, especially if we have this whole like encoding messages thing coming, and I'm telling you that there are some matrices that you cannot do it with because they don't have a matrix. We're already like, okay, well, we can't use non-square matrices because those will never work. Those never have inverses. But in the back of your head, you should be like, ding, 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 but wait a minute. If those aren't the only singular guys, well, how do we know if a matrix does or doesn't have an inverse? If we're going to learn 3 different ways to find inverses, we really would love to be able to know right away whether or not it has one, to be able to be like, no solution, don't have to do work on this problem, or, nope, there is a solution, I'm going to do the work and I'm going to get there. So in the back of our heads should be this question of, all right, these guys, the singular guys, they're going to have no solution for inverses. It's impossible to have. We got that the non-square are some of them. But how do we pick out the square ones that don't work? I'm not going to give you the answer. I'm going to have you guys just kind of be looking for it. We might see it this section. We might see it next section. Okay. So, if the directions say find the inverse of, let's assume that it has an inverse. Let's assume that it has an inverse. Here's one way of finding an inverse. And to be honest, for little baby ones, this is probably, I don't know if I should say the easiest, but it's not hard. But for bigger ones, it can be a lot harder. Ready? We can set up an equation and say, okay, this guy, this matrix, times another matrix needs to give me the identity. And we've done this in math all over the place. It's like, okay, well, if this guy has an inverse, that inverse times this guy needs to be the identity, and then let's work backwards. In math, a lot of times we try to like make a statement and then work backwards and try to make it fit. The problem is, what do we always do in math if we have unknowns? We make them variables. But wait, what size would this guy need to be if he undoes him?
2 by 2.
A 2 by 2. So can't I just say A, B, C, D? Because X, Y, Z.
Wouldn't the inverse
Let's
of
do
that
these ones.
just be -1, -4, 1, and 3?
Yeah.
You could try it, but I'm going to solve for it. I'm going to solve for it. We'll see if you guys, if your guess is right, and if we can always just do something that easy. My advice. You can't. Okay, so let's see why. Ready? How could I get that? Ooh, this is kind of like partial fractions in that we're taking what it needs to be and we're trying to set it up. Question, guys, what needs to make this 1? How do I multiply matrices? What would combine to make that 1? Nope. 1? Nope. 1 times 0. 1 times matrix multiplication. You guys just did a second ago. 1. 2A. 1A. 1 times A is 1A. So A plus 4C.
Yes, A to G.
Woo! I need A plus 4C to be 1. Why? Well, because matrix multiplication would say, remember, you multiply the first, cross down, and then add, multiply the seconds. So 1A plus 4C is what goes in that top left-hand corner. Now, how would I get the 0? 1B plus 4D. 1B plus 4D. Matrix multiplication. I know you have variables, but it's the same exact process. How do you get this bottom 0? Negative A. And then the next one would be? So here's the dealio. Matrix multiplication says, oh, okay, I get who would need to go where. The question is, how do I solve for what I don't know? How do I solve for A and C and B and D? You guys compare to the identity matrix. And I just started trying to show you a second ago. Can't I take these two and say, hey, I know who you need to be. A plus 4C, you need to be 1. And negative A minus 3C, you need to be. Don't I have a little baby system of equations?
Then
And then can't I take these two and say, oh, hey, I know stuff about you too. B plus 4D, you need to make 0, whereas negative B minus 3D, you need to make 1. Pause. What did I do to get all of these variables in all of these expressions? What did I do up here?
you just multiply.
Yeah, I just multiplied. It's just weird because it has variables instead of numbers, but I just multiplied. I multiplied and then I compared and said, well, I know what it's supposed to make, so let's see if your guys' ideas were correct. Because if you did, I don't know, what do you guys think, elimination? Looks nice to me, right? I end up with C equals 1. I end up with D equals 1. Then can't I back substitute? So then A equals negative 3. And B equals back substitute negative 4. Okay, double check. I did a lot of like plugging in and solving and back substituting. Ah, what's Sophia saying? What's she seeing? Why is she talking about them moving around? What would my new matrix be?
Or -3,
Can you guys compare this to the other two matrices that we saw were inverses a second ago? Alec and Sophia both were trying to do a pattern and be like, oh, isn't it just going to be? And now they're like,
Nice.
what?
It's like, why do the other ones be different?
But hold on, compared to the other two, there might be a pattern. If there's a pattern, that's awesome. Maybe we can use it. Do you see a pattern? Because, just a hint, they didn't all move. What pattern do you see? And then compare it to the other two and see if the same pattern exists. What do you think, Kat?
You like diagonally switch the top left and the bottom right, and the top right and the bottom left, and then make them make the 4 and the 1 different signs.
Check it with the other one. Is she right? The main diagonal? Ready? Is switch the main what? The main diagonal. You switch the main, switch the locations, right? And then why am I saying opposite the opposite? Opposite diagonal, what are you doing to them? Switching the signs. But I don't want to say switch because that's really confusing. So switch the main, switch the location of the main, and then opposite the opposite. And if you guys are looking at the original one that we had a second ago, switch the main, opposite the opposite. Or switch the main, and then opposite the opposite. Ooh, nice. So I wonder if this always works. You guys ready? So try. Find A inverse. Let's do B inverse. Why not? 4. B is equal to. Give me a second. I want you to make a guess as to what you think the inverse is, and I want you to solve for it on your calculator. And I'm going to do it the long way as I do both. I want you to take that one. Take the pattern that Cassie just found that worked for the first two that we did. Try to see what you think it is. Practice on your calculator using the inverse button. And meanwhile, I'm going to do it the longer way. -3 has, 5 has. Who's getting closer? Your guys' guess or my solving?
You're solving.
You didn't get close.
Double checking this fast. negative 3 halves, 2 over 2 plus 3 over 2 is 5 over 2 over 2 is 5 over 4. Yeah. So I'm getting 5/4, negative 3 halves, negative 1 half, and 1. Okay, now wait. Think. Because Cassie's not totally wrong. I took time to write out the pattern. You got partway there. You got partway there, just not all the way there. What did you guys think it was following the pattern?
5, negative 2, negative 3, and 2.
5, negative 3, negative
5, 2, negative 3, negative 2.
No,
Compare.
the 3 isn't on the bottom.
2. I was going to say this.
Hold on. Switch the name. Opposite the opposite. We only switch the name. There you go. There you go. Come on. Look at mine and look at yours. Look at mine and look at yours. Cassie had the right pattern, but her pattern will work sometimes. There's something else that will work all the time for 2x2s. What do you see extra that you needed?
Fraction stuffs.
Fraction steps? Hold on, double check my math. Did you guys find a mistake? I think I made one.
Might be better.
It should be 1/2, not 1.
Thanks. But why?
Oh, you went -2, so. Oh, you distributed 2 solid.
Oh, I distributed the negative and I didn't distribute things. I distributed 2 for some reason. That came out of nowhere.
It should be positive.
So then this is going to change B, yeah? Positive 1/2? And then B would end up equaling negative 3/4?
Yeah.
Good. Because otherwise the pattern wouldn't work. Now try. Whoop. Come on, what do you see? They're all divided by? So wait, he's divided by 4, he's divided by 4, he's divided by 4, 1/2, and he's divided by 4, negative 1/2? Well, where the heck did the 4 come from? And why wasn't he present a second ago for either of the other ones that you guys saw? How could you check? You guys know you can multiply and get the identity, right? Wait a minute, we already did this. No, we didn't. This is an alternate way. There's this term. There's this term coming. I'm going to show you one more method first. There's this term coming called a determinant. Very important in matrices. A determinant says multiply the main minus multiply the opposite. Think kind of like a dot product, but a subtraction instead. Multiply the main, multiply the opposite. Do you guys see Cassie's pattern of A and B switched and B and C became opposite? Is it there? Yes. But what's in front? Something extra. Is it there? Yes, but what's in front? Something extra. And actually, you know what? I don't totally mind. Let's just reorder our notes. I don't mind. We'll put this one next, because you guys picked out the pattern. We'll put this one next. There is this formula for finding an inverse, but do you guys see the dilemma as to why we can't just stop here and why I have other notes? This is a special formula, but it's only good for finding the inverse of a 2x2. Ah, bummer. And there are 3x3s and 4x4s and 5x5s that will be calling for us to figure out their inverse, and if we only have this, sadly, we're not going to get very far. But it's great for 2x2s. There is a shortcut for 2x2s, just it doesn't work for any other size. However, this determinant guy, well, he's super important. Remember how the dot product was super important for vectors? Determinants are super important for matrices. We're going to end with this page. We totally still have tomorrow to do this. I'm going to go back and peek at the calendar and try to give you guys a heads up as far as what's coming. This homework is not going to be due until... I struggle. We were originally going to try and have it due tomorrow, but it'll be due Wednesday. Not Thursday. It's not that long of a section. We're close. We're close. But we'll have it due on Wednesday. But tomorrow we do need to start section 8.4. But guys, the nice thing is section 8.4 says, hey, what's a determinant? And we're like, we already know that word. We'll need to go a little deeper. Alright, well kids, I'll see you later, alligators. Homework not due till Wednesday, but start tonight. I think I get most of it done. If you guys want to come back, I have chocolate bars, I have brownies. I guess my room is now the chocolate room. Don't know when that started. Because